anyone have an opportunity to read the handout material from last time? Can you share with the class what your current take is on what does precision healthcare mean, please?
It is going to need a more specific ability to diagnose individuals with respect to
Good.
the knowledge of the whole thing, your lifestyle, your genes, so that you can focus more on the actual gene mutation or the actual healthcare problem in a much more economical
No, I was,
bringing it down to a level.
Hi, we missed you at the class on Thursday.
Excuse me, boys and girls, that basically maybe 4 minutes long. And so I just thought it would be useful to start with it today and then jump back and dig just a little bit deeper into the brain. And then next week we'll get sort of, we'll pull back and look at it in a different kind of way. So this was produced and directed and formulated by the NIH. When it was done, I had an opportunity to be invited as one of their consultants, and it was just great fun to take all of this stuff and figure out how do you make it accessible to a teenager. So this was anticipating that the audience would likely be maybe high school kids or later. But you can be a PhD in any field and find it very interesting, light, and yet at the same time there is nothing in it that is humorous in a sense. It is to be taken quite seriously. So with no further ado, can you click on, there we go. identical to bananas. So, sobering thought. So the idea is that without going to school formally, without going into a laboratory, each of us on our gadgets can watch this thing 2 or 3 times and really understand something at a level that is very sophisticated. So I would urge you, because this went by, so to speak, quickly, you get a little bit of glimpse of it, but if you watch it a few times, it like soaks in, and all of a sudden you go from a complete person dropping down to a cell, and then chromosomes, and then DNA, and then these letters A, C, T, and G, and all of a sudden you start realizing, as you're sitting right now, in trillions of cells in your body, this is going on. As an idea floats in your mind, your neurons are playing with these sorts of things. It is amazing that there is a world, we can't see it, we can't touch it, it's not that kind of world, but it represents who we really are. And so I urge you to make some time to just indulge yourself in a cartoon that is loaded with gems and see if it actually changes the way you look at the world. Whether we're looking at leaves or flowers, they're doing the same thing. The rules of engagement are the same. So it opens up some really, really neat ways of thinking. So with my illustrious colleague, thank you.
Excuse me, did you mention how to access that on the computer?
Yeah, you just type in animated genome. That's it. And your search engine will do the work for you, and up will pop, and you'll see a group of things, and just click on it. So, in the context of all of this, some of us, how many people have had a little bit of a science background? Great, so about half of us. So, and the other half of us have sort of touched it along the way in one way or another. So we know from the field of physics that this room and our atmosphere and our bodies, all of this is a story of atoms. And many physicists with advanced and less advanced training deal with things that revolve around atoms and atom-atom interactions. And one of the mysteries of all of us is somewhere along the line, atoms became molecules on our planet, and that opened up the field of chemistry. And so all of a sudden, atoms were now in a different configuration. So it went from carbon, hydrogen, oxygen, phosphorus, sulfur as atoms, and all of a sudden it became molecules, and these molecules interacted with one another, and then some of us were in the field of biochemistry. So now it's chemistry plus bio to sort of create the development of microorganisms, plants, animals, so forth. Then these cells became tissues, and the tissues became organs, and the organs became organ systems. And 550 million years ago, vertebrates appear, and then they move along, and the human brain blossoms. And that's what we're using this afternoon to engage with some of these things. The brain is hungry. I mentioned last week, 20% of your diet is committed to the brain. It's also interesting that the brain is physically, if you can look at some of the maps and images that have been made, it's all organized in a three-dimensional unit. So the cells are 3D, the activities are 3D. It is a very dynamic three-dimensional activity. The other issue is that there are 80% of the brain is water. So all of these ingredients that we're using to think and reflect and make decisions with are 20%, and 80% is water. That's very sort of like disappointing in a sense, because it is really an amazing what this couple of billion cells, 86 billion neurons, 86 billion glial cells in 3-dimension, they're doing all of this stuff in an ambient environment that is 80% water. The other thing is that the brain uses 80% of the DNA. So it isn't like a few genes and we make a brain, it's 80% of everything that is in the human genome is used routinely by the brain. Kind of amazing. And then finally, we've got 80% of the brain in the subconscious. My metabolism is going on right now. I'm making some saliva as I'm speaking. I can hear sort of an ambient sound in the room kind of thing, so my hearing apparatus is bringing that in. I've got the visual joy of seeing all of you in your wonderful diversity, and that's coming into my visual system and being processed. All of that is going on. I'm not aware of it unless I make myself aware of it. So if I make some time during the day to meditate, that's sort of saying, I want to visit the subconscious and I want to reflect, feel the breeze on my skin, look at some plant that's opening up because it's spring in some part of the world, etc., etc. I mean, it's kind of, so we can go into the subconscious like a little bit, but most of it is on autopilot and we're completely oblivious. I'm walking forward and backward. Not a nervous thing, but I guess just a thing. I'm using my hands to express myself. It's sort of voluntary, but it's kind of subconscious. Many of us, depending on our backgrounds, we talk with our hands. If you tie our hands behind our back, we can't come up with anything. It's just the way we are, so forth. And then 20% the conscious, the big decisions, the innovations, the gifts of sort of seeing something that a lot of people could see, and yet seeing something that no one has ever realized before. And if you ever get a chance to go to Florence, about 1 mile just out of Florence is a little tiny town in which craftsmen have made 200 of the inventions of Leonardo da Vinci. I mean, it's remarkable. This guy is thinking about airplanes, there are no airplanes. Submarines, there are no submarines. I mean, the imagination, it's almost one of these things where, for those of us who were kids in maybe the 1950s, science fiction in the 1950s has become reality right now. There were people talking on cell phones, but there were no cell phones. You know, and on and on and on. Doors opened electronically, but, you know, and it's just remarkable that the human mind can envision something that no one has ever named. The word, when we were growing up, most of us in this room, the world was analog. I don't know that I ever heard anybody say analog then, and now it's digital. And this has happened in a lifetime, to go from one convention, which was very powerful, to this other convention, which is a little threatening, the artificial intelligence, machine learning, all of those kinds of things. Yes, please.
I don't know how many remember Dick Tracy
Mm-hmm.
and his watch. And his watch, he could, it's like the computer watches of today.
Yeah.
We thought it was crazy.
Yeah, exactly. So it's worth paying attention to science fiction.
What
Please.
is your brain doing while you're sleeping?
Working.
But is it at the same pace as?
It's
when
doing
you're
a couple,
conscious?
I mean, technically, you know, you can hook up electrodes and you can see neurological activity is taking place. And you can see parts of the brain that seem to be working a little bit more vigorously. But if you could drop down below the nerve impulse level and see what's going on, there is a phenomenon called neural pruning, where you are basically breaking down certain connections and rebuilding them in a different fashion. You're resting, we call it sleep, but sleep is a lot more than resting. It's a regeneration. Stem cells are becoming neurons or glial cells. Debris is being cleaned up. Some like housekeeping stuff is being done. Cells are replacing parts that were used up during the day, that we sort of overdid it with our multitasking or whatever is causing overactivity. All of that is nighttime. If we are deprived of sleep, we start being able to be functionless. We start getting lightheaded. We get incoherent. We start, it's sort of like being, what would be, you get lost. Let's say you're driving from here to Las Vegas, and you're in one of those funny places where there are no gas stations, no nothing, poor cell phone connection, all of that, and you're stuck in your car, and let's say you started walking, and it might take days walking to go from there to some place where there would be something. You would realize, without food and water, our brain doesn't do very well. And that essence, right now I'm feeling, I had breakfast, I had a snack a little while ago with Lois, and I'm kind of perky. But there's a point, we've all had this, where you skip breakfast, maybe you skip lunch, and it's in the afternoon, and you're a little out of it. And you know it. I mean, people around you may not notice it, but you know it. You're just not quite as sharp or as perky as you might be. So this just summarizes the context. Here, the reminder of this, the issue, Sigmund Freud is a good example, Jung is a very good example. A lot of people, sort of like, what's going on in the subconscious about who we are, about sexuality, about relationships, and all of these kinds of things. And there are many theories out there, and many of us have read some of those books and thought about it, that there seems to be an agenda that's going on at sleep time that we're grappling with. When we're sleeping, during the day we come up with a lot of ambiguity. Something's making us feel anxious. It's like stuff is, I forgot to call Irene. I was going to call Irene before I went to bed, but I didn't call her, and I'm laying in bed, and I'm preoccupied with, I didn't call Irene, and then I fall asleep eventually because I'm exhausted, and something is going on connected to Irene that I'm not quite aware of, and maybe I go into REM sleep, and in REM sleep, allegedly, is where we dream, and the dreams might last for seconds, and yet we think that they took hours, because we have a distorted sense of time when we think of the length of a dream, as opposed to when we're up and conscious and we're measuring how long this class is today. We can come up with a general idea, about an hour and a half, got it? But in a dream, it's sort of like, God, when we wake up in the morning and we're telling our mate, whoever we might live with, like, oh, God, last night, you can't believe it, I was dreaming about, fill in the blank, and it went on, and we did this, and so forth, and the whole thing, if somebody is monitoring it with electrodes and all of that, the whole thing could have happened in 2 seconds or 3 seconds, and when our memory of the memory, it went on forever. So this area is just fascinating, and of course, from some people, when either in the middle of the night, get up suddenly, and maybe some of you do this, and you have something going on that you determine is brilliant, and you want to write it down. Like oh my God, I got this unbelievable idea. I can convert carbon dioxide into oxygen, and my God, this could really be practical someday, and I'm going to write this down, and so forth. It's really quite interesting. I also mentioned some books last week. Just wanted to remind you, for those of you who love to read and are interested in the mind in particular, Life 3.0 by Max Tegmark, How to Create a Mind by Ray Kurzweil, and another book, The Singularity is Near When Humans Transcend Biology, again by Kurzweil. An interesting book called Evolving Ourselves, Redesigning the Future of Humanity, One Gene at a Time by Juan Enriquez. Unbelievable reads, scary, because it's a world that they're thinking about and writing about that is compelling young people who go to college to say, I want to major in the neurosciences, but I want to have a minor in artificial intelligence, and so I want to get something from maybe electrical engineering to study, and I want to learn about machine learning, and I want to go into that area. It is now becoming a really, really compelling area for a lot of young people who are seeing themselves as inventing the future in some fashion. And these books guide you very nicely into that world that is going on. Now, at the same time, we were driving here, and on one of the I can't remember which station we were listening to. It wasn't NPR.
KKK?
Might have been. And they were talking about some kind of a study came out from the American Psychology Association on masculinity. And the idea was there would be guidelines for masculinity and guidelines for femininity. And you know, so there would be like number 1, number 2, number 3, number 4, masculinity, and number 1, number so forth. Never did they really touch upon genetic variation. So it is kind of amazing that everyone in this room, if we could magically do the genome, the complete DNA sequence on everyone in the room, they would be 99.9% identical. Whether you were a woman, whether you were a man, whether you were big or small, whether you were African American, Latino, Asian, Caucasian, whatever you were. 99.9% identical. That means that the variance is 0.1%. It turns out that that 0.1% is a number 3 million A's, C's, T's, and G's. So, in terms of words like masculinity, these, you almost intuitively know that in that 0.1% is where a lot of variation comes up, our personality, our intelligence, our sensibilities, our empathy, our compassion, whatever criteria we might come up with are tucked into 0.1% of the human genome. This is a very hard concept to fully integrate into yourselves because it is so much easier to group people about race or about the color of their skin or something, red hair, no hair at all. I mean, whatever it is, we can group that way, but the idea of really saying, of course there's variation. Of course there's going to be a gradient. Of course we are not identical. We're near identical, but the 0.1% is the celebration of our diversity. So we come along as we, about 150,000 years ago. At the moment, there's somewhere above 7 billion of us on the planet Earth. And so whether we're Islamic or Jewish or Christian or Buddhist or Zen or zero. We're here, and we think a little bit different. We respond to challenges a little bit different, but that's it. And then these concepts of genomics, phenomics. Now, phenomics is the expression of a gene activity. So my blood pressure, my cholesterol level would be phenotype. My balding, phenotype. My blue eyes, phenotype, et cetera, et cetera. So phenotype is like the product of what the genes have done, and then the genes, the genotype, is essentially the storybook. It is the parts list of life. So phenotype are all of the physical, behavioral, and biochemical characteristics of an organism. Originally noticed by Gregor Mendel in peas. They're yellow, they're green, they're wrinkled, they're smooth, they're big, they're small, was the universe he was working in to come up with some of the concepts that we still count on today. Our blood type, blood chemistry that is done when we go to the physician for an annual checkup. They take some blood, they look at a collection of molecules that can be identified in the blood rather easily, and that's all phenotype. Genotype is the genetic makeup of an organism. And so genotype lives in the mitochondria that we inherit only from our mother. So the mitochondria that comes from our mother has a genotype. Mitochondria have about 37 genes encoded in each of those organelles called a mitochondria. Then the other genome is that we all bathe and groom ourselves and so forth, but we're walking around with about 4 pounds of microorganisms. They're lining our gut, they're on our skin, they're on our hair, they're everywhere, and for the most part, they are symbiotic. We live in harmony, they help digest our food, they maintain the balance of pH in our GI tract, going from very acidic in our tummy to more alkaline in the large intestines. All of that is dealt with by these bacteria that live in our bodies. And then finally, the human biome is you just add the whole thing together. So all of the somatic cells, all of the germ cells, all of the mitochondria, all of that DNA, and then all of the DNA from the viruses and bacteria and yeast that are living in or on our body, and all of that is called the human biome. What I'm doing, I hope it's not overwhelming, is we're building a vocabulary that we can get more comfortable with as we move along. So here's an example of early experiments in which, and again with animals in a laboratory setting, you can do manipulations. And so here, by messing around with the length of chromosomes, in this case in a fruit fly, Drosophila melanogaster, in this particular example of breeding, you could produce a wrinkled wing every time. In the other examples, through breeding, you retained some of the body shapes. So we've got genes going in our brain. We have an enzyme that is facilitating gene function, and we're able to visually look at these sorts of things in a high-powered electron microscope in 3D at the moment. And this is the anatomy of every gene. They all start with an enhancer. So this means, and then followed by a promoter, then followed by coding regions called exons, with spaces in between called introns, and then they all have a terminator. a
Is
little
that a
tiny.
telomere, the Terminator? We use
Terminator
the word telomere?
is 3 letters, like 3 A's, and it means stop. So it's the stop signal so that you can then move on to another gene to express it. So the enhancer and promoter work like air conditioning system in this room where they can adjust to how much output. So are we going to just trickle out a little bit of gene activity of, let's say, one of my favorite genes, globin? A little bit of globin or gushing globin. You know, we need max. So the ability to do that is regulated by the promoter enhancer regions. These are a series of 5 to 15 letters that just happen to be there, and you can, when you're using computer technology to scan all of the A's and C's and T's and G's, this helps you determine, here comes a gene. I can see there's an enhancer and a promoter and coding regions and introns and whoops, stop. Okay, got it. And so that's how eventually the human genome was decoded. So in 2018, last year, there were more than 3 million regulatory elements that control the coding part of DNA. Coding means that's the action, that's where the real stuff is located. So here, looking at the brain, this 3-pound, 80% water, loaded with neurons and glial cells, what can it really do? Well, it deals with sight and smell and hearing and taste and touch and chewing and swallowing, plus integrating whatever goes on. So that's its function. So somehow, and the somehow is a big question, somehow, starting with single-cell bacteria 3 billion years ago, by trial and error, mistakes taken routinely, the changing physical environment, it's raining, it's snowing, the land masses are moving here and there and everywhere in that whole wild world with an oxygen-rich atmosphere. This organism evolved, and today it is our tool. And not only is it our tool, we have the capacity today to change evolution. And that's exciting if you're 18, 19, 20 years old. And it is sobering if you are a mature adult at a different part of the lifespan. Now, inside every cell in your body, it kind of looks like this. Again, it's always water, like a lot of isotonic saline solution in every cell. But the movement of activity is molecule to molecule to molecule. And it means that one molecule touches another molecule, and all of a sudden a phosphate group is moved from one molecule to another. And so we go from AMP, mono, to ADP, di, to a try something, and that reaction of adding 1 and then 2 and then 3 groups is very important if you're producing chemical energy in a biological system. But the process is these networks of molecules that are aligned in water, so to speak, to be able to propagate these different signals. So if you think of it in a more mechanical sense, they are very closely integrated, some of them being more visible than others. My wife gave me a gift a number of years ago that I still have and won't part with, and it's a clock, and it runs on batteries, and it's all gears. And some of the gears are such that if you're watching the clock, you can literally see the gear move. And at the same time, there are gears that you could sit there and look, and it's like, nothing's going on, and yet, yes, they are moving, but it's imperceptible. And I think the spirit of the gift, as I recall, is really everybody matters. You know, whether you're a big contributor or a little contributor to the big scene, we all matter. And it was a wonderful reminder. And so here is an example in two dimension of something that is exquisite, just exquisite, that is going on in which molecules in 3 dimension are organized and have the wherewithal to do a certain set of functions that in the larger sense allowed Leonardo da Vinci to blossom, or someone more recent, James Watson, Francis Crick, in what they were doing, Alan Turing, in the decoding. Every once in a while, a human being comes along with Martin Luther King memory, as they come along with this extraordinary set of gifts. And those gifts, when put to use, you know, just dazzle. They're just truly remarkable. So here, looking at a human brain and some of the parts of it, and then the DNA, and if some of the DNA, an A is substituted by a G or a C, something like that, it's a mistake, and hopefully the mistake doesn't turn into a disease, but every once in a while it becomes PKU, Tay-Sachs, schizophrenia, bipolar disorders, depression, Down syndrome, dementia, and cerebrovascular stroke, etc. Amazing. How can the DNA work, replace itself, propagate itself so precisely, and at the same time, if there's one mistake, one of the letters of the 3 billion letters is mistaken, it has this problem. So human brain, 3 pounds, could easily fit in the palm of your hand or between. Arguably the most remarkable organ system that has ever evolved. It beats hands and feet and heart and lungs because of the many, many remarkable things that it can do. It takes 25 years to develop. So it means if you've ever had a teenager in your home and they seem irrational, and they're 15 years old, and they've just finished telling you that they are smart and you're not. If you've ever had any of those kind of experiences, something's going on that we're not always sensitive to. They have not yet finished forming their brain, and they've got a lot of hormones and self-assertion substituting for real judgment and insight and so forth. We've got 10 trillion somatic cells in our bodies. At the end of the first 2 years of life, I don't know how many of you can remember that. For me, it was like really, really, it's a great reflection. I remember sitting there and all of a sudden, neural pruning started going on, and I was losing all of my synapses, but my mother, whose name was Clara, very nicely kept stimulating me with new things in the crib, and somehow I was able to continue along my journey. Neural pruning can reduce the number of synapses by 50%, and you don't even know what's going on. I mean, it's like invisible. And yet, in the course of life, whether it's being 2 years old, or again in adolescence, or again midlife crisis for some of us in our late 40s or 50s, neural pruning saves the day. And these synapses respond to stimuli from the outside. The brain doesn't have the ability to, in a sense, generate synapses for the hell of it. It's always connected to a stimuli. And this is one of the simple reasons why we need each other. We need each other at a biological level as well as a political level and all of the rest of it. We need to be stimulated. And when we're alone, we can do a certain amount. We could paint or mess with music and, you know, we could be a librarian. We could do all kinds of wonderful things. But it's really interesting that we need human beings. Thank you.
Do you want to take a break now?
Huh? No, I'm good.
Why do we have neural trimming at the age of 2?
No one knows. No one knows.
And then
It could be
are we-
that that there's some kind of a mechanism that is activated when you get to some number, and maybe by the time we get to 2, we've like used up all of the neuronal connections, which means trillions of them. But there is something's going on, and when they say 2, it's literally almost to the month. But you don't, if you know the what do they call the terrible twos? That it may be that as a parent dealing with kids and how incorrigible and irrational they might be, maybe it's part of this. I don't know.
Quick question.
Yes.
The last paragraph, it says synapses respond to environmental stimulus.
Yes.
Does that affect the loss of synapses, the environmental factors?
Yeah.
Is that the epigenetic layer
Yeah.
is degrading?
Not because of who you are, but because of the importance of the subject matter. A woman, I'm blocking on her name, a woman wrote an article in the New York Times Sunday edition, comes with a magazine referred to as the New York Times Magazine. And there was an article in which she proposed, sort of as a hypothesis, that racism is an epigenetic stimuli, and that the epigenetic factors, this is at the chemistry level, to methylate or demethylate cytosine or guanosine, but at that level, something happens. It influences RNA production and DNA activity and all of that kind of stuff. And, this was her prediction, and it's inheritable. So the idea that we know about boys and girls, and we know about getting overheated, and we know about sexual activity, and we know about, reproduction. What is much more difficult to really understand is that something, according to this hypothesis, that racism is an example of environmental stimuli, and whatever happens in the individual can be inherited from generation to generation. And with racism, sort of thinking, I'm making up a number, 500 years of it, or 700 years of it, depending on where, when and where you begin, it could be. So I wasn't the only one who read this article, and a number of scientists have jumped on it and have come up with some really very real data, and have come up with a very interesting clinical information. One type of clinical information is African American reproductive women, wealthy or poor, educated or not, have the highest prevalence of low birth weight premature babies, and babies that sometimes die in the first year of life. So the normal thinking is, if you're well educated and affluent, this isn't going to happen. And if you're poor, poor people seem to get all the bad things, so that makes sense. But this defies that. And there's certain other things that were raised with that, coming up with the assertion that epigenetics is the reason, because it is not unusual for the woman who has that episode, low birth weight, premature baby, that her daughter or her daughter's daughter will replicate that particular behavior. So it means that today, in 2019, epigenetics, as well as traditional genetics, as well as microbial genetics, are at play. And we need to understand that and integrate that if we're going to do something with it. Instead of making these superficial judgments, your kind of people, you're from Sardinia, in the lower boot of Italy, you're always going to be farmers. You're only going to be farmers. But this group over here, the intelligentsia from your ancestors are
From Ireland.
Ireland. Bad example. Japan, you get the idea. Yeah.
Is this true of other marginalized groups? Let's think about the untouchables in India.
Sure.
You wonder if they
Sure.
have low birth weight
Oh, no, the low birth weight, I mean, they might, I don't know that that group has been
Well, I
looked
mean, you
at.
wonder if it's, we talk about racism, but there's also, like in Ireland, if you were Protestant, you hated Catholics. I
Right.
mean,
Mhm.
you wonder if that gets encoded in the DNA too.
It's a good, I mean, it's a
Or
good.
the Jews in Europe.
Yeah. Yeah, we have many, many examples. Famine,
Or trauma.
World War II, rounding up Japanese people, putting them into these camps because they're Japanese, they were born in America, raised in America, they're Americans. Nevertheless, you just can't trust these people, and you do this kind of thing.
Well, you wonder if they could go
There's
back
gotta
into
be-
a study and see if they had low birth weight children in the camps.
Mhm. Yeah, but I mean, the low birth weight premature babies would be a phenotype of something. But there are many others, depression, certain attributes that people have as a consequence of these experiences. The famine, the pandemic of 1912, viral infection, 47 million people died and so forth. Those of us who grew up around polio and the polio story and so forth. These are all potential epigenetic influences. Yeah, please.
Well, I was just going to ask, when you speak of racism, I'm wondering if a sense of self and the psychology surrounding ego could be
Sure.
an impact.
Yeah, self-esteem, ego. Many people for centuries never having a real family. Other people for centuries always having a family. So it opens up a lot of questions. I mean, it's hard to get answers, specific answers to these questions, but I think all of us should be sensitive to that epigenetics is real. It's not going to go away. It has profound importance, and we need to respect it because it opens up, when you're playing with the 0.1% of the traditional molecules of DNA, that's the playing field. But when you go to epigenetics, it makes it much larger, and the variations become much more profound, and the significance, I mean, something like sickle cell anemia is a terrible genetic disease. It affects one letter change. It produces sickle cell. Well, if you happen to live in Africa,
It's useful.
then you can stay alive and reproduce before you pass. And so it is an asset in terms of biological thinking and evolution, and makes sense. But it doesn't make any sense here. But the time between living in Africa with malaria to now, well, malaria still is cooking in Africa, and sickle cell in Africa is still helping people reproduce, etc. So, it's your place on the planet is not the place you want to make all your judgments from, especially standing in San Marino as a very privileged community. It is a very different position to look at the larger world than if you go to Madrid or one of the cities of New Delhi, go down to Brasilia. There's so many other possibilities. Here's a couple of genes. The names again, do not always really make much sense. This one is Notch2NL in the cerebral cortex, located on chromosome 1Q, the Q arm, and mutations often attention deficit disorder, autism spectrum, anxiety, and so forth. So the ability to go from a human neurological disease to a gene and locate the gene on a particular chromosome is no small feat. And then the trick is the treatment for any of these conditions going to end up being something that can address the mutation on that particular gene, on that particular chromosome. So if you're in the pharmaceutical industry, you're thinking, and depending, something like autism affects a very large number of people, as do some of these other conditions, you start thinking about, what kind of money should we put out to do R&D? Where is the NIH at with respect to research and development? How can we get the smart people together, and could we come up with some therapy for somebody born and raised with autism that would really be significant? So this is just looking at those genes again, and in terms of their development, microcephaly, small brain, macrocephaly, larger brain, influenced by Notch 2. These two guys, James Watson, Francis Crick, heralded, remarkable, talented, and abrasive all at the same time. It just comes with the territory. And I don't know if any of you are interested, but there is a fascinating documentary called something like The American Experience, which focuses on James Watson as a racist. And he believed that certain people, African American people was one that he used, are just inferior. Intelligence and so forth. And of course, he was, at the time, called himself the Chancellor of the laboratory at Cold Spring Harbor, and there were African American postdocs and PhDs and all of this kind of stuff. And so in a sense, this discovery that he made, this looking at a metallic model of the X-ray diffraction that was done by Rosalind Franklin, and that they borrowed and interpreted and made this three-dimensional model of DNA, adding the significance of it's a double helix, and the units called purines are held together by some kind of hydrogen bond, and they are limited to A, C, T, and G, adenine, thymidine, cytosine, and guanine. Fantastic discovery, contribution. And James Watson, the taller guy on our, the smaller guy on our left, was all of 25 years of age. So from 25, and he was like maybe 32 when he got the Nobel Prize. So he had this rather unusual early years. He graduated from the University of Chicago. I think he was 17 or 18 years old. I mean, he kind of got a really great start. But the sad thing is he's alive now. He's in his either late 80s or early 90s, and what a pathetic creature he is with these racist comments and so forth. But it's part of it. So anyway, they made that observation. This I thought you would be interested in. This is from the National Academy of Sciences. And those of you who have children or grandchildren or just some friend with children, this is the new biology. So instead of the biology where we'll go to the tide pools and look at the creatures in the tide pools and touch them and squeeze them, or we'll dissect a frog and we'll look at the distribution of India ink and learn maybe about the immune system, kind of observational. Biology was originally an observational experience. Today, with mathematics and engineering and computer science and the physical, chemical, and biological sciences, and this really speaks to the need for all of us. I mean, hypothetically, we're all in kindergarten, that all of us need a fundamental education before we take an on-ramp or off-ramp into a profession. But the way the world is at the moment, you know, people are thinking, okay, this is my daughter and she's going to be a lawyer, and so that's it. And I'm not sure about you, but you're in, you know, I mean, it's like it's predetermined, or a teacher in a classroom. Those of you who are from Mexico, you're never going to amount to anything, so we're not even going to bother with you. And I mean, the power of adults on children that shape what that child aspires to become or not, it's phenomenal. And yet we as a society, we seem to be very inconsistent, or kind of miss a couple of cities along the way. Really fantastic. So in order to really be able to engage in this kind of subject, it's not all about chemistry, it's not all about biochemistry, it's not all about neurosciences, and yet you need enough of a background to get a little bit from these different fields. And this is an attempt. So this is the so-called recommended curriculum for the 21st century by the National Academy of Sciences. Here again, this is this picture was taken from my mouth. Those are cells from my oral mucosa. We added a little calcium chloride. The cells pop open, releasing the chromosomes. I have a normal amount of chromosomes. And then this is a map that can be generated. The map is a series of letters, and these letters are held together by hydrogen bonds. And it's called hybridization when you take one strand and another strand, and they've got A's and C's and T's and G's, and that they somehow find each other and they bond specifically by that pairing. So A is always looking for T and vice versa, and C is always looking for G and vice versa.
And are you saying an A can't get with a C?
Can.
Or
Preference is the T. But if somehow the affinity of these are interrupted somehow, ionizing radiation, ultraviolet light, something in making new DNA molecules. And out of that, well, here's just a little brief background. This is at the level of chromosomes. This would be 1941, 1942 biology. So we know for sure that those of us with 2X chromosomes are a female. And then there are males with an X and a Y. As this Y chromosome is very tiny, and certain women assert that that's why men just sort of like miss the point very often in a debate or a discussion. Sometimes with the two chromosomes, one of them disappears, and when it does, this is a woman who only has one X chromosome. She's alive, she's viable, she's very tall and very thin, and the condition is Turner's syndrome. That would be an example of the missing. Then a deletion. This is chromosome 5, a pair of them, and a piece of them breaks off. Again, it breaks off because of radiation or UV light or something like that. And that injury is called Cri-du-Chat syndrome. Very serious, life-threatening syndrome in which it is caused by those genes that live in the piece of the DNA of that chromosome that have broken off. This one we're generally familiar with. This is Down's syndrome, in which an individual has 3 chromosome 21. This one happened in Japan during World War II with the dropping of the atomic bomb on Nagasaki and Hiroshima. and the bomb dropped and lots of people died and there was a lot of damage. One of the things that happened biologically to people who lived after this calamity is that chromosome 22, a piece of it, and a piece of chromosome 9 reconvened and formed, and when they did, it produced chronic myelogenous leukemia, sometimes called adult leukemia, and to this day, in communities with ancestors from that activity, leukemia pops up with a very high prevalence. So we've got all of these, a deletion, a duplication, there's a lot of things that, yes?
Okay, can you go back to the other slide? I just want to understand. You said that chromosome 22 and chromosome 9
Yes, pieces of it, yes.
rearranged, and now the outcome is chronic myelogenous leukemia?
Uh-huh.
That's what my father died of. So when was this discovery made regarding this pattern? Was it
I'm
recent?
guessing like the early 1960s.
Oh,
I mean,
really?
the event happened, of course, in
Well, I know that happened right
1945.
after World War II, but
Now this, the one of the things, and it may pertain, in 1945, that era,
yes.
people in the military thought that it was okay to go swimming from the ships, this is like Navy people, from the ships, which the water was filled with radiation, but they didn't know the seriousness of swimming in radiated water. So these bombs, there was first the testing of the bombs on some of these islands in the South Pacific, and then the real bombs at Nagasaki and Hiroshima.
Right.
But today we know from Chernobyl and more recently the tsunami and the breakdown in Sendai in Japan, that events that happen, 12,000 miles away from here, with water movement and with atmosphere, move around the globe. It's not clear always what the pattern of distribution is going to be, but it's possible that this radiation events in certain parts of the world got into the air and moved around and might have affected other people. The testing that were done in Nevada and Utah by our military during that period of time might account for it.
Do we know if this, I'll call it a mutation, happens in living people whose genes recombine when you're exposed to this, or does it only happen in the act of reproduction and we make new genes?
Well, when it first happened, it happened in somatic cells only.
As in,
Terms
within
of,
one person, not in the act of combining?
no, I mean, millions of people were affected. All of them did not come down with this rearrangement. Those that did come down and could be, I diagnosed rather early on with chronic myelogenous leukemia. It would have been somatic cells, lymphocytes, and
So
so
it's not
forth.
necessarily the children of those exposed, people who were exposed
And, no,
had this recombination.
no. So the people's somatic cells, their lymphocytes, blah, 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 were affected. And those of them that had reproductive capacity, their germ cells were also affected.
I guess I'm again asking.
So that
did this-
it could be propagated. Babies are born with this condition.
Understand that. Did it happen within one individual before they reproduced? Or did it only, in other words, because this isn't just a transcription error, this is all genes splicing. and stuff.
Chromosomes.
Chromosomes.
Yeah.
So I'm just wondering if that happened inside individuals or only in the act of reproduction.
I don't know. I could only really use my imagination to, sort of
Well,
see what was going on in these cities when the bombs dropped.
Well, I guess if a survivor comes down with this disease would answer the question, or if only the children of survivors had it.
Now, this actually became an epidemic.
Of those who were present on the ground, not just their children. That's what I was asking.
Yeah.
Thank you.
Yes?
Could you say a similar thing could be happening to the young people that are fighting in wars with post-traumatic stress syndrome?
Well, the people who are, being maybe too candid, in World War II, when people were injured, seriously injured, very often they died. The healthcare, sort of like on that expression, in the field, was not very good. And so these injuries, basically, they didn't come home, they were dead. Today, the advances that have been made in the field of healthcare are really remarkable. And we are now able to keep alive people who have been traumatized, who would have died in World War II, but today they come home. And it's now, numbers are, in many, many, many thousands of people in that category. Minimally, they've got an epigenetic change in their life. Minimally. And again, depending on the nature of what happened, for some people, it's almost like football players. Those of us who were riveted over the weekend to the Saints and the Rams, and then the Patriots and whoever they played. The clashing of the helmets, the heads. I mean, it's almost like watching a boxing match, except they're wearing, like a costume, allegedly to protect themselves. The idea of epigenetic effects going with concussion is well established. And of course, in Iraq and Afghanistan and so forth, large numbers of people were exposed to a concussion. That would be like maybe minimal. And then there are concussions plus I lost a limb, or I lost 2 limbs, or I had huge facial surgery, et cetera, et cetera. So I mean, there's a whole collection of things that our men and women come home with from this modern military engagement. Please.
I looked it up and it says it's not, you can't pass it on to your children, which I thought was interesting. According to the website for leukemia. Because I was wondering, that's CML, and then the other leukemia that my mother has, it's 93, she has the chronic, everyday type of leukemia.
Yeah.
And I wondered if that could be passed on, so if this one isn't passed on, can that?
Yeah, I'll double check, because children are born with leukemia. I'll see what
It says it's
the
rare.
nuance might be.
Yeah.
Thank you. So let's, you're having a good time. Is everybody comfortable? We'll march on a little bit?
Yes.
Okay, so we're 20 to 2. So imagine we're in a library, and this is a library, but it's called, instead of the Caldwell Library, this is just called Genome. And if you can imagine that a book in the library is the equivalent of a chromosome. So library, like for some of us when we were kids, we got the Encyclopedia Britannica, and that would have been the library. And then you pull one out, A or B or C, and that would be called a chromosome. And then from that, the words that you look at on the page, each word is a gene. And then the gene is made out of letters A, C, T, and G. So in a sense, that's one way, not the only way, but one way to think about genomics and the levels of organization. So in a normal individual, and then I just retyped this and made 2 or 3 little errors in the letters, and it would be a patient. So the convenience that many of us got excited about is that the digital revolution was yielding computer technology, high speed, lots of storage spaces and all of this kind of stuff while this was going on. So biology and information met because of computer technology, and basically DNA is referred to as the book of life. It's the parts list of life for whatever the species might be. if you look at the chromosomes, the individual books, we have 22 pair plus the sex chromosomes, in this case, X and Y. The human genome is 2 to 4% Neanderthal, 8% viral, and 98.5% human. Only 1.5% of the DNA is literally 6 feet long in a cell. So if you could imagine a piece of spaghetti that is 6 feet long and it's all mushed up and into like chromosomes, the percent of it that is actually functional material, coding regions, is 1.5% of the total. So the obvious question is, what does the rest of the DNA do? Over here, we have 21,000 genes, okay? 21,000 genes, human being. We also contain 11,000 non-processed genes and 8,000 processed genes that are never expressed. So we're walking around with some stuff that is only there because of evolution and a sort of maybe not such an anal approach to cleaning out anything we don't use. So we do have some things that we don't use. So at the level of doing business, here is a cartoon type thing of the alignment between the two strands of DNA, and a mutation is a mistake in any one of these letters not matching the right letter. So this opens up, we could call it misspelling or substitution, misrepresentation, and due to that, we get this is sort of classical images that I put together, but if you were a very young audience, this would mean nothing to you. But these are faces of people who really made a difference in our lives, for sure. And the variance between any two of those people is 0.1%. So these letters, we call them SNPs, single nucleotide polymorphism. So that means it should be an A, but it's a T, or it should be a G, but it's a C. It's that kind of thing. It's a polymorphism. Here's an example of just a little abbreviated person one of us. We have a particular sequence and we're perfectly normal and everything's cooking and we're just fine. Somebody else, the T, the A in person 1 has been substituted by a T. It causes a slight aberration, but it's not clinical and it's no big deal. And if we have it, we don't even know we have it. And the third example is, instead of a T substituting for an A, we have now a C substituting for the A. Now we have a disease. And the disease could be life-threatening, it could be one of many, many things. It could be a cancer, it could be a respiratory disease. Here is the big example of such an example. So here, we're looking at chromosome number 11, and we're looking at the sequence of DNA, and we notice that the T, there's an A in the normal that's been substituted by a T, and when that takes place, we get sickle red blood cells instead of these normal donut-looking red blood cells. So a disorder like sickle cell anemia is a point mutation in a single nucleotide that happens many, many thousands and thousands of years ago. Yes?
In neuro diseases like MS or Parkinson's, could that be from an insult, a traumatic thing that happened, or a natural mutation because it's found in the family, not just one person? It usually isn't. There's inheritance.
Number 2,
The second.
the mutation. Yeah.
Okay,
So not that long ago, this is 2001, these two publications came out just a couple of days apart, and each of them contained the 95% draft of the human genome. One done by the federal government, the one in Nature, and one done by a private company, Craig Venter being the CEO, published in Science. As soon as you know how to do one, obviously, let's try another. So in 2005, the chimpanzee was done. And again, all of this becomes very useful. The macaque genome was done in 2007. Today, it's like a zoo. Today, there are literally hundreds and hundreds of different kinds of animals in which the genomes have been done. And in human beings, we have about 25,000 human beings with complete genomes on record, and we have another 200,000 or 300,000 with partial genomes on record. So in this case, genes in the DNA, 21,009 of them, are transcribed into RNA that's called the transcriptome, which in turn are translated into proteins called the proteome, and the system, as you could readily see. And a little simple cartoon, and this was also found in the paper handed out at our last meeting, going through the different activities, so you have a feeling for that. A couple of concepts have come out that are kind of interesting. This strikes a lot of people as being weird. We have 200,000 different proteins in our body, but we only have 21,000 genes. So the original storyline was one gene, one messenger, one protein can't be correct. So somehow it's possible to get more than one product out of genes. And because they're spaced, as we saw in the little cartoon, with exons and introns, they can be spliced and rearranged. And when that's done, we can come up with very interesting areas. Here, the kind of thing that strikes me is zebrafish, 85% homology, homology being exactly the same, 41% homology with bananas, 7% with E. coli, the bacteria that live in our gut, which again speaks to the profound importance of evolution, that we are incremental and we consist of some of the things that worked a long time ago, and they're held and perpetuated. The brain is being looked at in 3 dimensions by a number of people. The Allen brain, Allen recently passed away, was one of the founders of Microsoft, very, very owned, I guess, basketball team, football team, so forth. Very, very unusual guy. That is available for all of the genes. All of us are involved with this. And here is an example of monozygotic twins that differ from one another as much as 30% by 60 years of age. One has schizophrenia, one doesn't. But they are, at the DNA level, identical. Opens up the opportunity to look at twins for epigenetic changes, because the DNA isn't going to change necessarily, and that of course has been done, is being done. So here's a twin study looking at the unaffected versus the affected brains of a schizophrenic twin and an unaffected twin. And so this is using a non-invasive technology to look at phenotype and be able to tell them apart. Panic disorder, monozygotic twins versus dizygotic. They're like fraternal twins, that comparison, really quite striking. And then, of course, it raises what specifically in the chemistry of epigenetic changes is taking place, and is there a way to develop therapy to address that along the way? Opens up some wonderful opportunities. These are some of those relationships. So of all of the things that are going on, all it takes is one substitution or misspelling to cause some pretty serious diseases. And these SNPs are being well recorded. And so genes seem to appear in primates about 3.5 million years ago, and then going through speech and language and Duchenne and Huntington's and Parkinson's and ALS, and all of these are connected with very well-documented mutations. My mother had schizophrenia before she passed. It went to about 10 years, and I was very anxious to see, did I carry the ApoE gene, which is one of the signature markers for schizophrenia of a certain variety. Fortunately, I don't, but it was a big concern. Then the autism and schizophrenia have a number of mutations in common. Parkinson's, a number of disease mutations in these genes: alpha, synuclein, Parkin, DJ1, PINK1, LRRK2, and GABA, GBA. Mutations are associated with Parkinson's in those situations. Sleep and the circadian rhythm of sleep, also subject to mutations. Some of us live on 5 hours of sleep. Some of us need 9 hours of sleep. You know, it goes. It's not like everybody needs exactly this or gets the same amount of sleep. Stages of sleep also regulated by genes. Sleep disorders in America now running $411 billion a year in medications and so forth. Obstructive sleep apnea, very, very common, especially in men over 50. Then the development of drugs that either make us feel good or not. Dopamine is a very important one. This is what dopamine chemistry looks like on the board, and it's released from our neurons under certain circumstances like physical exercise. God, I walked a lot today, and God, I feel higher than a kite. Well, it's dopamine. Or I've been sitting on the couch and I'm really depressed and I'm loaded with serotonin. So drug addiction and the neurochemistry of drug addiction, a lot of people are looking at the details of that and how to treat it in a sophisticated way. This is an example of hearing, our ability to hear, our range of hearing, all under genetic control. Mutations that cause us to be deaf or not process certain sounds built into this biology. These are the cells that are crucial. These are hair cells, and this is an image of two people, a healthy young person and somebody who went to too many rock concerts and didn't pay attention to how loud the sounds were. So as you can see, the cells are not doing very well. They're damaged, and it's a permanent damage. The biochemistry of hearing. Here are some markers that have been discovered in 2017 as markers for autism. These are all markers that are for Alzheimer's. And this is something that I'm closing with that's kind of interesting. At the end of every chromosome, the unit is called, this unit, it's called the telomere. So every chromosome has a telomere at the end of every chromosome. There is an enzyme called telomerase that basically chips away at it as we age. And it's so well controlled that by looking at the chromosome, you can, and carefully, you can determine how old someone is, like plus or minus a year or two. It's a very significant indicator. Most human diseases are aging related, as we can all attest to. So this area, some people decide to really look very hard at it, and there's a subtelomere region which is located which contains a lot of cytosine and guanosine. These are the two nucleotides that are modified with epigenetics. It's where they're methylated or hypermethylated in the course of life. So we now know precisely the part of the chromosome that is most sensitive to an environmental insult like racism or famine or war or locking up thousands of people, or the children at the border that came up from Guatemala, Honduras, very likely, in the scheme of things, have an acquired epigenetic challenge. Too young to deal with adjusting to that environment. Yes, please.
Is it worth having your telomeres checked?
It's sort of academic.
And because there's nothing you can do about it.
No, not yet. There's a company in Palo Alto called Geron, for gerontology, and their mission is to figure out how to inhibit the enzyme telomerase from chipping away at the end, the subtelomere, so that you essentially would slow down the biological aging process. And they've been around now for about 15 years, so they have enough money, but I don't know that they have a product to ship. It's still the promise in startups, as some of you may know. It's a lot of it is driven by hope. If we just could raise another 10 million, 15 million, because it's very expensive to be able to get there. We're so close, and all of a sudden 10 years went by. This is not trivial science. But anyway, it's interesting how much we do know at the moment. Here's at a larger area. So all of our cells, when our cells divide in our body, which they're doing right now while we're all sitting together, all of this is going on very, very nicely.
Can we go back? You mentioned there's a impact of hearing on biochemistry. Is there and you mentioned permanent damage. So, for example, if your sleep is disrupted, you're saying that there's a physical effect? If there's, let's say, constant noise while you're sleeping, constant talking.
In the draconian military sense, sleep deprivation is a tool to break down the executive decision-making of an individual to get at information. So nurses in ERs, I'm on a shift, but the person who's supposed to cover for me got in a car accident, is going to be delayed, I'm exhausted, but I got to hang in there. I got to hold this particular position. Intern, resident, all of this, pilots. So the need to give yourself a break, or your work to give you a break, is imperative. And one of the funny things it's not funny, one of the things going on with the strike that we're in is, when you think of the precision of the people's judgment who are in the towers at LAX for guiding in planes and guiding out planes, if they are sleep deprived because there are not enough of them to cover, and on and on and on, it obviously puts a lot of people at risk. And I don't know how they make the call when we got enough, because most, especially since it's dominated by men rarely sort of are wimpy in the sense of, I can't, you really have to let me sleep. Rather, I could do I'll do one more 8-hour shift. So it's well, it is
So
what
is that
it is.
why, that's a tactic in POW camps? I've heard in POW camps or in incarcerated facilities, constant noise, constant disruption?
You know,
Is that a
You know, the
tactic?
story, I mean, the people who lived through World War II sort of kind of like zipped it up and didn't talk about it, and it was considered, you know, not appropriate to do that. And yet, many of them, either themselves or others, lived through this stuff. I'm just thinking of, you know, if you went to Auschwitz or Buchenwald.
Yeah.
From what I understand, these were not resorts. This was, whether it was the noise, whether it was killing, I mean, whether it was just fear, that all had to do something with epigenetic influences that, I mean, most of those people are now dying off from World War II, soldiers as well as the people who were in prison, but those that are still alive, it's pretty remarkable that they're still alive, when you think of it. So we are at the bewitching time. Any other questions? And if not, we'll see one another next week, same time, same place.